Fine. Now, rotations. I've shown you what might be called some applications of the concept of rotation. There is one special case. There is one special case of rotation which appears to be rather rather useful in certain special circumstances. It is what is referred to as a half turn. Half turn, let me mention that. So it is a half turn. A half turn is merely a half turn is really just a rotation. So let's say about some point P. The angle is spatial, it's pi. So, well, exactly what this means is the following. You have one point P, which is fixed, and apart from P, if you take any point X, then the image of that point is simply obtained by joining P and X and producing it until you reach a point X prime, so that P is the point, the fixed point P is really the midpoint of the line segment X prime. Okay, so let me repeat that. So for instance, if you take a point Y, okay, its image under the half turn with center P is obtained by simply joining the point Y to the point P and extending the line segment until you reach a point Y prime, so that P is the midpoint of the line segment Y prime. Okay, so of course, I mean its very definition is that you are rotating the line segment PX through 180 degrees. You are rotating the line segment PY through 180 degrees. Okay, so that's how we can look at it. That's how we can. Okay. So that's half turn. To define a half turn, all you have to do, since the angle is fixed, it's 180 degrees. So you talk about a half turn. Okay, so that's a notation. It really doesn't. Half turn about the point, about a given point P. So that's the expression. Okay. Now I will give you an application in which this half turn thing is predominant. It's rather nice. Now I would like to point out one thing there in connection with half turn. Now please notice that if X goes into X prime and Y goes into Y prime, then if you join the points X, Y, X prime, Y prime, X prime, and X, Y prime. Now this is clearly a parallelogram. And the point P is the center of the parallelogram. That's to say, the point in which the two diagonals of the parallelogram intersect. Now please bear this in mind. Now I would like to present you a theorem which is, okay, so that's my fourth, fifth, sixth application, let's say. Application number six. It is the following. This is in fact a rather useful result, and it is in fact a rather beautiful generalization of the triangle inequality actually. So it simply says the following: if you take any, in fact, quadrilateral, but I'm sort of restricting my attention to convex quadrilaterals. Let's say A, B, C, D. Okay, and if you if let's say, if you take the midpoint of AD, and if you take the midpoint of BC, so let's say, for instance, the midpoint of BC is, let's say, S, and midpoint of D is T, let's say. So you've got this line segment. So you've got this line segment joining S and T. The theorem is that the line segment, so the length of the line segment, okay, so yeah, the sum of the lengths AB and CD, in fact, exceeds twice the length of the line segment ST, S and T being D, S and T being, okay, so let me write this more clearly. I don't want, okay. Okay, so this is, in a minute you will realize that, by the way, I'm not quite sure if I have made myself clear. I mean, of course, if this quadrilateral happens to be a trapezoid, that's if the sides AB and CD are parallel. If they're parallel, then of course equality occurs. Yet we have to be a little bit careful. We have to be a little careful about that. So I wait a little before I tell you when equality occurs. Okay, equality occurs if and only if. So let me write this. Equality occurs if and only if. I shall write this later. I shall give it later. It will. This necessary and sufficient condition will, in fact, become. It will actually become obvious as I proceed to give you the proof. The proof. Okay. So let me take. Okay. So let me. I will just take a slightly larger picture. So okay. So that's DA, something like this. I don't want to draw it too large, and I will draw line segments instead of straight lines. Okay, something like this, more or less. Okay, so this is the vertex. Let this be the vertex A. Let this be the vertex B, a little bit longer, perhaps. Okay. And that is, okay, so perhaps something rather like this. Okay, yeah, that I think that should do. You know, it is, I attach a lot of importance to obtaining picture which will make a lasting impression on your mind. I think that certain configurations have that power. Yeah, so that's, I'm trying to okay, so that's why I'm being so careful about choosing things. Okay, so there we are. Okay, so the midpoints S and T, the midpoint of BC, is it the midpoint? Yes. That's S, and that's the midpoint T. Okay. So let me join them and indicate the line segment that will be of importance for us. Okay, so, okay, I don't mind announcing straight away. In fact, I have already told you that this thing can be seen as an extension of the triangle inequality. So I will make some transformations. Predominantly transformations. And of course, the half turns will make their appearance quite frequently, quite powerfully in this proof. I will turn this problem somehow into a problem in which you can read the required inequality as triangle inequality. Okay? And I do it as follows. I consider a half turn. Okay, so let's consider a half turn with its center at S. Okay? So everything turns 180 degrees about the point S. So for instance, the point T moves into a position like this. Now that's something I have to be careful about. Okay, so that's not an easy configuration to put on the blackboard. Okay, so this piece is equal to this piece, and in fact I choose T prime in such a way T prime. Okay, so I have taken a half turn with center S, so that of course the point T goes into a new point T prime. Okay, but of course, C, it's not interesting. C goes into B, and of course that there is obvious. By the way, this is a half turn is, we have already encountered the term. This is an involutive map. So if a half turn brings the point X into X prime, the very same half turn will bring X prime back to X. Okay, so if this is called phi, then phi applied twice will give the identity map. So so if C goes to B under this half turn, and B will go to C as well. So that's what we have. Okay, and what happens to the point D? Well, D will also turn into a point, and that point will be a new point, of course. It's not a point that is already in our configuration. Now, observe the way, thinking in terms of Euclidean transformations, rotations or translations or half turns, as in this case, how thinking that way introduces new points into your configuration, which somehow, although they are new, and although they seem to be coming out of your sleeve, have really a lot of bearing on the problem you are solving. Okay, so that's D prime, something like this. Right, so D prime T. Okay, simplification. Okay, so this piece, and this piece are of course equal. Okay, so clearly this piece and this piece are equal. Yeah, so we have got the following situation. So, and of course, since this piece and this piece are equal, so AT and D prime T prime are two vectors which point in the same direction. So it means that, okay, so let me perhaps make these dotted lines, okay, so as to indicate that they do not actually belong to the original picture, but they have been, in fact, introduced. They have been introduced by, are inspired by Euclidean rotations. So there we are. Okay, now we observe, finally, we observe the fact that if I join A and D prime, then, okay, here we are. Şu nesne çocuklar, bakın. This thing is a parallelogram, right? I'm writing it down. TA D prime, TA D prime, T prime is a parallelogram. Okay, it's a parallelogram. Well, actually, we are finished because you see. Now let me use a little bit of color to illustrate. You see, we are interested in two lengths, AB. This is the length AB. Let me indicate that in red. And the other length I'm interested in is CD. But you see, the half turn with center S has turned C into B, D into D prime. So this length CD is in fact exactly the length BD prime. Çocuklar, do you now see the lights? Şu üçgene bakar mısınız? Just look at this triangle. In this triangle, one side is AB, the other side is BD prime, which is the same as CD, and the third side is AD prime, which is one side of the parallelogram AD prime, T prime, T, and the side that's opposite is in fact TT prime. And what's TT prime? T prime is obtained from the point T by a half turn about S. So these two line segments, this piece, TS, and ST prime are the same. So in fact, the length of TT prime or the length of AD prime is in fact twice ST. So the triangle inequality in the triangle ABD prime tells me that AB plus BD is definitely larger than AD prime, which is twice ST. Okay, so the proof. So proof. AB plus CD. Değil mi? AB plus CD, which is the same as AB plus BD prime. And that is, of course, larger than AD prime. But AD prime is exactly the same as TT prime. But TT prime is exactly twice ST. We are done, finished. That's done. But that's a beautiful interplay of standard tricks of elementary geometry seen, well, as the effect of half turns, so on and so forth. Okay, so that's rather nice, and I have obtained the inequality. Now let's go back and ask the question: when does equality occur? So the equality occurs. The equality, that's to say, the length of AB and the length of CD added together will give you exactly twice ST. This happens if and only if the triangle inequality in the triangle BAD prime reduces to a equality. When does that happen? When in a triangle, the triangle inequality, okay, so let's say A, B, C. The triangle inequality is that B plus C is always larger than A. When does B plus C become equal to A? Well, that happens, okay, that happens if and only if your triangle actually degenerates into a line segment and the vertex A actually creeps into a point. Okay, so let me do it like this. A on the line segment BC. So in order for the triangle inequality to become degenerate, your triangle must in fact collapse into a line segment. It must become degenerate. And of course that's not the whole story. It must become in a way degenerate so that okay, for instance, in this case, the point A must occupy a position on the line BC between the points B and C. So, in this case, you must have this point B must in fact lie on AD prime. Well, that's great. Well, in that case, BD prime, which is parallel to DC, must coincide with the direction of AB. So it is ABD prime. They must lie on a single line, and that must be parallel to CD. So that means if and only, okay, so here we are. So if and only if the line AB is parallel to CD, so that ABCD is in fact a trapezoid. Trapezoid. It must be a trapezoid, but that's not all. That's not all. You must also make clear that the point B is in fact between A and D prime. So what does that mean? It means that the vectors AB and CD must point in the same direction. So you must have this kind of situation, this kind of trapezoid. You must have this kind of trapezoid. Okay, so AB must point in the same direction as DC. Okay, so let's do it like this. AB must point in the same. What you must preclude, you must say, well, that can't happen. It should be this. You should not have something like this. That's CD and AB. That should not happen. And in fact, this shall give you what's called a reentrant. Okay, so this is, we don't want this. We want this. Okay, essentially it boils down to the following, that this inequality holds, and in fact, inequality reduces to an equality if and only if your quadrilateral is a trapezoid. Properly speaking, a non-reentrant trapezoid. Okay, so that's the whole story. Right. So how much time do I have left? Now that is the wonderful thing about this. Okay, so you can solve this problem in many different ways. The wonderful thing about looking at this problem by means of half turns, or let's say Euclidean transformation, is that the inequality, the geometric configuration actually transforms nicely, and actually it shows us how the thing boils down to a triangle and the triangle inequality. So this whole thing is, initially, your attention is all over the place. You've got this quadrilateral, the line segment joining the midpoint, so on and so forth. So you've got a rather strange inequality. But now, looking at it through half turns, your attention is suddenly concentrated on the triangle ABT prime, and then you simply apply the triangle inequality. That's all that there is to it. So that is how initially people have worked with transformations. Actually, we have got quite a bit of time, but the piece that I have got to give you now is rather lengthy, so perhaps it might be a good idea. Okay. So let me start and spend another 10 minutes, then we shall go. Okay, I've got a few things to say. Let me remind you something. On Monday, I shall be teaching, I shall be lecturing, okay? That's 1 hour. Perhaps I shall be solving some problems too. And I shall be, of course, in my office after the lecture, which is all very fine. And I would like you to attend the class especially because it is evaluation time. It is important that you evaluate lectures, for bad or for good. I mean, please do come and and give your opinion about my lecture. Give your opinion about all lectures. Presently, we have no way of detecting and doing something about bad teaching in this institution, except these evaluations. If they are properly done, they might help us, okay? So take evaluation seriously. And on Monday, my lecture will be evaluated. Do come along. Do give voice to your criticisms or your praise, your eulogy, whatever it is. Anyhow, do be around. I shall be terribly annoyed about people who do not attend on Monday. So I expect you to be all correct and present on Monday. Anyhow, now let me, so to speak, introduce the subject that I shall take up on Monday. I don't want to go deeply into it because, as I said, it's rather a lengthy piece. Okay, so I have introduced what? Well, the very basic transformations about which I think every primary school is familiar with: translation, with rotation, half turn, what else did we do? Reflection, so on and so forth. Now, I would like to ask the following question. What are the compositions of? Okay, so what happens if you, for instance, compositions of Euclidean transformations? Once again, I refuse to make a systematic, I refuse to make an, so to speak, an exhaustive study of the thing. I shall merely point out certain special cases, and I shall use them in solving problems. And I hope you will agree with me in the end that using some basic facts about the compositions of Euclidean transformations, you can give really spectacular solutions to some problems. Compositions of Euclidean transformations. So that's what I'm going to do next. And I shall ask, okay, so let me ask one question and answer it, then we can call it a day. Transformations. So, and I shall continue this on Monday. Okay. So let's ask, for instance, the following question. What is, okay, so the reflection. Okay, so what happens? What's the, what is? Very simply, what is? If you take a reflection in some line K, and if you follow it by yet another reflection in L, what happens? What happens exactly? Well, the answer to this question is rather important. It is. Let me take the. Okay, so there will be two cases, two possibilities. Case one, there will be two cases. Case one. The case one is the case in which K and L are parallel. So, what I am doing is I am looking at two parallel lines. I'm looking at two parallel lines. And so this is K and this is L. And I'm taking a point, let's say X. And I'm taking its reflection first in K. Okay? Let's say I reach the point X prime. And then I take the reflection of X prime in the second line, L, and I reach the point Y. What is this composition? Well, in the case when the lines are parallel, it's easy to decide about it. Okay, so clearly the line K can be obtained, the line L can be obtained from the line K by a translation. So let's say there is in fact a vector that sends, okay, so I would like to imagine that vector which is perpendicular to both of them, a vector perpendicular to both lines, U, which sends, and let me assume that the translation, so let L, the line L, be obtained from K by a translation. Did we? Okay, by a translation through a vector U. Okay, so K moves into L by a translation through vector U. Okay, so if that is the case, so let's look at what happens to X. You see, okay, so let's take the point. Okay, so if you drop a perpendicular from X onto K, let the foot of the perpendicular be P. And okay, so X prime, drop a perpendicular onto L, let this be point be Q. Şimdi çocuklar, clearly, if you look at this thing, clearly the length, of course, XP and the length XQ are the same. And of course, clearly the lengths X prime Q and XY are the same. So in fact, you see, the vector that joins X to Y is really twice the vector that sends K into L. So this is 2U. So in fact, that means, so we have come to the conclusion that if you reflect, if you take the reflection in a line K, and if you follow it by a reflection in a line L, which is parallel to K, and in fact L is obtained from K by a translation about the vector U, then the result is in fact translation by the vector 2y's U. Okay, so I put a frame around this to indicate that this is rather interesting. So this is the case 1. This is case 1. So it's rather interesting. Yet another interesting thing about this thing, this observation is that, in fact, I can take any translation and I can decompose it into 2 reflections. In fact, okay, so let me make the remark. In fact, conversely, any translation can be expressed as a composition of 2 reflections. This is actually the beginning of a very important and beautiful story. It will turn out that all distance preserving Euclidean transformations, all, so to speak, congruences will be it will be possible to express all congruences, all distance-preserving Euclidean transformations as combinations of reflections. What does this remind you of? In algebra, there is a result which is very similar to this. You know, a reflection is a transitive thing. In algebra, you've got permutation groups. Do you remember them? Permutation of n objects. And there is one permutation which is very specific. It's the permutation. So you've got n objects. You are looking at the permutations of n objects. If you pick up 2 objects, and if you look at the permutation that interchanges them and leaves everything fixed, it's got a special name. What's called? It's called a transposition. And in fact, you can prove that any permutation can be expressed as a concatenation of transpositions. Now that is strongly reminiscent of what happens in Euclidean geometry. It turns out that not only translations, but all sorts of Euclidean transformations can be expressed as concatenation of reflections. Transpositions are involutive too. If you apply a transposition twice, it gets you, so it interchanges 2 points. If you apply it twice, it interchanges them back into original position again. So, you know, transpositions of the algebra of group theory, transpositions in group theory of permutation group are rather like the reflections of Euclidean geometry. Okay, all permutations can be obtained as concatenation of transpositions, and all Euclidean transformations, Euclidean congruences can be obtained as concatenation of reflections. So that's a similarity which underlines the importance of involutivity. Involutive maps are important in algebra as well as in geometry. Okay, let's stop here, and then I shall see you on Monday.